In the previous two lessons, we covered the fit functions and callbacks functions, and we dived into the model checkpoint and TensorBoard callback arguments. In these lessons, we will continue with the fit functions and move on to the last callback argument, and that is early stopping. Let's go ahead and get started. Early stopping monitors the performance of a model for every epoch, and it will terminate the training when a monitor's matrix has stopped improving. Let's assume the goal of a training is to minimize the loss. With that, the matrix to be monitored would be a loss value, and then the mode would be a minimum, because we are talking about a minimization of the loss. So a fit function training loop will check for every epoch at the end of every epoch whether the loss is no longer decreasing, considering the mean deltas and also patience if applicable. Once it's found no longer decreasing, the trainings will be terminated. The quantities to be monitored needs to be available in the logs dictionary. In that case, to do so, we need to pass the loss or matrix at compiles. That means the loss or matrix in the compiles have to be aligned with the fit functions in order for us to use this early stopping argument. Early stopping is a very powerful regularization technique to tackle the overfitting problems. Let's take a look on this graph. As the epoch goes by, the training errors and validation errors naturally goes down. But after a while, the validation errors stops decreasing and reverse. This indicates that the model has started to overfit. However, in many cases, the training errors continues decreasing. Therefore, in practice, it's much more effective if early stopping is applied to monitor the performance of the validation set, that is the red lines right here, during the trainings. Once we spot that there's an increasing or reverse in the validations curve, we will then stop the training. Commonly used arguments includes includes the monitors, what kind of quantities that you are going to monitor, and also the mean deltas, that is the minimum changes in the monitored quantities as an improvement. So say, for example, that is the absolute changes of something less than the mean delta. So that the models will keep on the current status and then check with the previous status, and then to calculate the delta. That is the changes, whether it's less than the absolute changes that we defined, or is still more than that absolute changes that we defined. If that is less than the absolute changes that we defined, then we will consider that it has no improvement at all. On the other hand, there's a patience, that is a number of epochs with no improvement, after which trainings will be stopped. Say, for example, we have a patience for 5 epochs. If within that 5 epochs there's no improvement, then we will stop the training. And there's a mode, just like what I mentioned before. In the mean mode, we are talking about the minimizations of the loss. In the max mode, we are talking about the maximizations of the loss. So that depends on the quantities that you are monitoring. And in auto mode, the directions is automatically inferred from the name of the monitored quantity. Say, for example, the name is accuracy, then it will automatically to help you to pick up the max, something like that. Now, let's take a look on the example. First thing first, we are going to import the sequential model, import the dense layer, import the NumPy, and then also from the callback, we are going to import the early stopping. And we also, again, we use this simple network as an example. We have the 3 inputs and then 1 output. So use the random functions to pick up some random numbers. Now just run this out. Now we are ready to define the callbacks arguments, that is the early stoppings or loss with patient. Now we can configure the neural network. We use the sequential functions, and then in the first layer we are going to have 2 neurons, and then in the last layer we are going to have 1 neuron with their corresponding activations functions. And of course we can compile the functions with Adams as the optimizers, MSE as the loss functions, and MAE as the metrics. And we can run this cell. And for the early stopping functions, we are going to monitor the loss values. That means we are going to monitor this MSE, mean squared error. And with patience equals to 3, that means if these MSE are not decreasing in 3 epochs, then we will stop, we will terminate the training. And then we just assign it to the name early stopping callback. And then we can put everything into the fit functions. And then here you can see that's the X, Y are the inputs and outputs, and then the epoch are equals to 200. And then we use 80% of the training data, 20% as the validation data. And finally, we just put the callbacks equals inside a list with these early stopping callback as the argument. And if I train it, and you can see it will stop around 170 runs epoch, because in this case, we are going to use this mean squared error value. This is the mean squared error value because it has not been improved in the last 3 epochs. So we will just terminate the training. Remember what I mentioned before, it's always recommended to use the validation loss. This is the validation loss instead of the loss to monitor the metrics, to monitor the training. It's mainly because you can see that the validation's loss will have will stop decreasing and reverse at certain points before the trainings becomes overfitted. However, the training curve will continue to decrease. Therefore, if we monitor the loss functions, it somehow cannot help us to avoid the overfitting issue. Instead, we always use the validations curve to avoid the overfitting. In that case, again, we use the same we configure the same neural network as shown here. But for this times, let me run this cell first. But for this times, we are going to change this to the validation loss, monitor this validation loss instead of this loss, and then wait for 3 epochs until it terminates the training. Now again, if I run this cell, and you can see that the training stopped it because at around 88 epoch, because the validation loss are not improved. That means we are quite overfitted in the previous case, because we overfitted around more than doubles of the epoch. But at here, we stopped the training around 88 epoch. Therefore, in our previous cases, it's obviously that it has been overfitted. But for this case, because we are using the validations loss to monitor the training performance, so we avoid that issue. For the next example is that we are going to use the minimum deltas to, instead of the patience, to do the early stopping. So just in case, if the validation loss is not improved by 0.00001, in that case, we will stop the training. Now let's take a look on that. Again, we just configured the neural network as what we've done before, and then we assign these early stopping functions, but instead of the patience equals to 3 for this time, we change this to mean deltas equals to this 0.00001. And again, we just put this into the put everything into the fit functions. And now let's run the cell. For this time, the training stopped at around 100 epoch. And in this case, you can see that the validation loss has not been improved more than this value, more than this 0.00001 value. So in that case, we stop the training. And in the last two examples, you can see no matter I'm using the patience or I'm using the mean delta, the overfitting issue can be avoided if we monitor the validation loss instead of the loss. And that's it for this video. In the last 3 videos, we talked about the commonly used callbacks arguments under the fit functions. In the next video, I will talk about another important argument under the fit functions, which is the batch size. See you in the next video. Bye-bye.